Hello, I'm Simon, also known as Polyhop. Welcome to this tutorial on top instancing in TouchDesigner. Please note we are using TouchDesigner version 2023-11600, so if you're using a newer or older version, it might not work in exactly the same way. Thank you to all my Patreon supporters, and a special thanks to my top supporters for helping make this happen. Through my Patreon, you can gain access to project files, a private Discord channel, vote on future tutorial topics, and more. Today we'll be looking at how to create this donut or torus of cubes using instancing. I've done an instancing tutorial in the past that focused primarily on chops and some tops. However, since then, TouchDesigner has added the support for tops going directly into instancing. So I wanted to update that tutorial and kind of show what my current workflow looks like more often than not. If you're unfamiliar with instancing, it's a way that we can take geometry and draw it many times in our rendered output. This is much more efficient than, say, using something like copy, soft, which will quickly get heavy, especially if you're trying to animate or move your copies. So this not only leverages the GPU, but it also, I think, is a relatively intuitive way to work once you get the hang of it. Using instancing, we can not only translate moving our instances in XYZ, we can rotate them, scale them. I'm not doing it in this tutorial, but you can also adjust color, texture, all sorts of aspects of them on an instance-to-instance basis. So each one can have varied qualities, which makes them really powerful for creating complex and varied geometric scenes. We'll also look at how to create this attractor, where our instances are affected by their proximity to a point moving in 3D space. Before we jump into creating our torus, I want to talk a little bit about different operator families as they pertain to instancing. So specifically, we can instance using tops, chops, sops, and dacts as our driving the different qualities, and we can use these in different combinations as well. So I want to just look at the difference with that, and also the relationship between how you can coordinate those instances between different families. So let's start with a grid SOP, and I'll start by making this 4x4 in my rows and columns. You don't have to follow along with this necessarily. It's more informational, but feel free to do so if that helps you. Let's hit A and then W to show the wireframe view, just so we can see what we're looking at here. And I'm going to convert this into a few different families. So I'll add a null. From this null, let's go from SOP to chop. Add a null. Let's go from this null to tops with chop to top. There's not a way to go directly from SOPs to tops, so you always will have to go to chops first. In our top here, we can also set this to RGB, since we have X, Y, and Z values, and we want our RGB values are going to be storing those positions. And we'll create a null here. And then lastly, let's just go from SOPs to DATs. So now we also have the index of that point. We can see P0, 1, and 2 is our position, and our point width and our normals. Okay, so now we have a null for each family, and they are containing pretty much the same information. Some things are containing less information. So these are not containing things like not that these are different, but there's some additional SOP information that is not contained in our chop or top. However, for our purposes, that doesn't matter. So let's look at instancing. Let's create a rectangle. I'm going to make it a bit smaller so that it will fit in this grid. Right click to add a geocomp that will automatically connect an in and an out. And you'll see that it has added the render and the display flag automatically. This is a good way to create instancing networks where you can swap inputs easily in and out if you want to play with different geometry. On our instancing page here, let's turn on instancing on our geocomp, and we'll start by instancing our chop. So dragging null2 over to our default, and I will have to match the names of the chop channels. So TX, I can type TYTZ if I'd like. And if we hit open viewer, I did that wrong, TXTYTZ. Here we go. Additionally, just so that we can see what we're doing, I'll split this screen with Alt left bracket and hit Alt 3, which can also be done here for the geometry viewer. Okay. So you'll see we're drawing a rectangle at each one of these positions. It starts at -0.5 and -0.5, which is the bottom left, moving across the X horizontally. And then each time it finishes a row, we're moving up 1 in the Y-axis. Now this is important because it tells us how this channel, which contains 16 samples, corresponds to the order of our instances. These different families they all pretty much operate in a similar way, but I just want to point out these differences. So the next thing we could do is we could use our top to color it. And you'll see that it's dark in the bottom left and yellow in the top right. It's because our color information is also position. So this is actually negative values and positive values, red being our X and green being our Y. So when they're mixed, we get yellow. If we set this chop to rows fit to square, nothing happens here, but we actually see a corresponding grid. I can see that better by pressing A to open viewer and N for normalized split. I can also hit D to display pixel values and to hover over each pixel for its value. One other thing to note, specifically about tops, it's really the one that can do this, is if we go to point clouds, there's a point repack tool. And this is more of a hypothetical, but if we set this to 2x8, you'll notice that it doesn't really care what the resolution is here as long as the number of pixels line up with the same number of samples in my chop. If I set this to 2x2, we get an error because we don't have the same number of instances in all of our inputs. Additionally, this does tell us that, the order that we're reading this is left to right and bottom to top. So 0th instance up to, in this case, our 16th or 15th instance if we're doing 0 indexed. And it stays the same. So when it does repack this, it automatically keeps that same reading direction. However, if we did flop this with a flip and we wrote essentially like flop it on its side, then suddenly our relationship between the color and the position is broken. So you have to keep in mind, typically it won't be a big deal as long as you're not doing things like flopping your data. So the other point here is that we can use these other nulls, could use SOPs or DATs and have an identical result. So if I wanted to, I should be able to color it here. Nothing will happen immediately, but I could choose P0, P1, P2, and see the same result. Again, just coloring it based on my position. And likewise, if I wanted to translate using SOPs instead of chops, I'll drop that in. Again, name changes. So this is also P0, P1, and P2. So they all can be interchanged, though there's different reasons that you would use different operators. And I do think that Tops are especially nice because they are calculated on your GPU, so they can often provide really efficient processing, especially when you're dealing with large numbers of instances. So now that we've looked at the different operator families and how they pertain to the process of instancing, let's specifically take a look at tops and how we can use those to create our particle donut. We want to start off by going to the palette and grabbing from the point cloud section the point generator. Drag that on. And I'll close the palette since we don't need that. It'll give us some more space. So this is a super useful tool for doing instancing in tops. It gives you a range of different shapes and forms and will generate a point cloud. And the output will be in tops. So this right here, if I change to viewer smoothness nearest pixel, each one of these pixels corresponds to the XYZ position of one of these points. So RGB is equivalent to XYZ, which is how we want to start thinking about our grids of pixels when dealing with instancing, whether it's rotation, velocity, position, scale. These values are not just something to render and look at, but a place to store data. Looking at our point generator, one thing we have is a num points. We might not want this to be too high depending on your system, but I'll leave it at 10,000 for the moment. I will collapse these. So you'll see in my example, I selected and right-clicked and chose collapse right there. I had everything in a container that can make it a little bit more useful, or a base rather, a little more useful for reusing. You could eventually put it in your palette if you want to have a tool that does this. So I recommend starting there. Let's call it something useful like particle donut, whatever you'd like, really. And I will also customize this and going inside of it, let's add num points to the top just in case we want to change that. So I'll drag that into parameters and choose bind new pair as master. So those two are linked. Now on the top layer, I have num points. Additionally, I want to set the shape to torus surface. And I will set the second radius value here to 0.4. So the first value defines the radius of the torus. The second value determines the radius of this inner ring. This is the same behavior of the torus SOP if you've used that before. Next, let's actually hook this up to instancing something. So I will call this null POS for position. And then let's create a box. And if we look back at our points here for a second, we'll see that this is a little bit larger than -1 to 1. In fact, if we hit A and then N for a normalized split, we can see it goes from a roughly -1.4 to 1.4. So if these boxes are 1 by 1, that's a little bit too big. So you can either change this on the scale or all of these values to 0.4 so that we have a much smaller box. I will again right-click and choose geometry comp to automatically hook up a geometry comp to our SOP. And on the instancing page, for instancing, turn that on and drag position to our translate op. Now I can type RGB, which corresponds to our XYZ positions. And if I do open up this viewer, whoop, there we go. We have ourselves instanced boxes at our points. So far, so good. Let us also create a render network over here so that we can render that as a top and see what we're doing on the right while we work. So I'll add a render top set the resolution 1080 by 1080. I also will add a camera comp. I'll add a light. That's looking better. And I can add an out, which will automatically show us what's in, going out of this operator or the space. I'll also turn on the display flag with this little blue dot. And I don't like having my display flags show up behind my network. It makes it hard for me to read them. So I'm going to split this pane left and right. I like the keyboard shortcut Alt left bracket, and then additionally Alt 4, or just use the caret for the top viewer. Drag this over, and then on the left, right click, display, and turn off backdrop tops. All right, now we can see what's going on. Lastly, I do want a material, so I'm going to add a thong. It's currently a thong, but it's just a default thong that we can't adjust. So let's drop this onto our geo, and we might change this later, but for now we can leave it as is. Cool, so let's now make this a little more interesting. I want the positions to not just conform exactly to this shape, but let's add a little bit of noise to vary their position. I can do this by right-clicking and adding a noise top inline, and immediately get some dramatic effect here. This is currently set to monochrome, so it's translating, if we hit A and then V, all of my points in this diagonal, because monochrome sets each channel RGB to the same value. So anytime it pushes it up, it's going up in every single axis, which is why you get that diagonal look. Let's turn off monochrome. And now you can see it's also, looking at the 3D, you can kind of tell a little bit better. It's also offset around 0.5, 0.5, 0.5, which is our offset. You'll see here it's up a little bit, right, and to the right. So bringing that down to 0 moves the entire system to closer to the origin. And additionally, I can bring up or down my amplitude to vary the intensity of the noise. You can see it more clearly now. If I move the offset, the whole torus shifts. So I will set this to eventually something much smaller. But before I do, I want to talk a little bit about this second input here called noise coordinate map. By default, let's go back to our regular view and set this to just viewer matters, nearest pixel. A little bit about what that means. So by default, our noise is using a 0 to 1 and 0 to 1 EOV or coordinate map. And so that means that pixels that are next to one another in this gridded view have similar, they're related in terms of like the noise. What that means, let's look at a noise chop first. With things like sparse or Hermite, or in the context of our SOP simplex or Perlin noise, those different noise algorithms have they're pseudo-random, so they're going to be deterministic based on a given seed, but appear sort of random, so it's good for creating like unpredictable feeling results. And with adjacent samples, so in this case we have 1D noise or one-dimensional noise, adjacent samples, they don't vary in extreme ways. They are related to their adjacent values of the previous and the next sample, so that we don't have a dramatic change in slope. I mean, we still are getting these peaks and these valleys, which we can control with some of our parameters, but we're not getting extreme discontinuities. If we change to a random type, now we're seeing every single sample, it doesn't really care what the last value was. It's generating a new pseudo-random value. This can be useful for other reasons. But however, if we want things to change gradually, but still feel like it has unpredictability to it, we would probably go for something like sparse noise. Similarly, with our noise top, normal map, our noise top, we have a similar degree of like slight change between adjacent values. That's why it looks more like clouds here. And it's both in the vertical and the horizontal axes. If we switch this to random, we're getting something that feels a lot more like our one-dimensional noise did. The adjacent values are wildly different. And again, if we varied the seed here, it would look more like white noise, less like clouds. So in our case, if we're dealing with 3D or 4D noise, that 3D also means that in addition to translating it in the X and the Y axis, which we can visibly see moving forward and backwards, we can translate it in the Z or even in the W direction. That's a fourth dimension. So it's hard to tell when you're looking at it in this view, but if we turn off monochrome and set this to 32-bit float so we can have negative values, hit A and then V, and I'll also bring this to 0, the offset. Now, if I transform in that Z axis, you should be able to sort of see it. It's hard to see at this period, but it will, wrong values there. You can start to see it's shifting in these different axes. Z is always harder to tell what's going on. But partly that's because this is in relation to this grid. So the default is defaulting to the position of the pixel in this grid. And if you think about our torus, these pixels, this is our point, they're not necessarily next to one another in 3D space, even if they're next to each other in the pixel grid. So just in this instance, it makes sense that we're seeing a grid that's warped because essentially we're getting kind of like a slow, gradual shift between adjacent pixels. And so we should be seeing that relationship maintained between the two. In fact, if we change our resolution of this noise to something like 256 by 10, we'll now start seeing a narrow strip of 10 by 256. So that hopefully starts to make some sense as to how this grid relates to our final noise in 3D. However, for our donut, we can use this noise coordinate map, and this says, okay, take the second input here and use that as the X, Y, Z, and even W for our alpha as the noise coordinate. So it's looking up that noise, feeding that into the system, so that adjacent values here will have the same kind of smoothness that we're seeing, and not just adjacent, but that it's related to how far away they are in this 3D space. So if we just feed that into the noise coordinate map, it doesn't seem dramatic right now, but if we increase the period to say 11, now we can see it's much more, the actual variance sort of corresponds much closer to the form of our pixels. And even transforming it in Z, it sort of is, it's like pushing towards you. It's a little bit hard to see, but it has a smoother variation, whereas if we did not have this connection, you're going to get something that feels doesn't quite make as much sense as we move these forward. A lot more chaotic, and it doesn't really relate to the position of these points in space. So Hopefully that starts to make a little bit of sense, but just to know that oftentimes you can feed in your input positions to get noise that conforms to your XYZ points. Okay, so let's get moving forward. So some other things that we want to do is add rotation to this system. So I'll quickly go in and dial this back down. I don't want this to be really that high, so 0.7 for my period, 0.02, just to add a little bit of variance here. The next thing I'll do is copy this. And one thing I actually missed noting here, by default, our noise is added to the input. If we just choose noise, it's pretty small, right? But we do want this to be set to input plus noise. Whereas our rotation values, let's just set that simply to noise, because we don't want to mix our position into our rotation. We do want to map it to that noise coordinate, and the first input will also give us the exact same resolution. So it can be handy to just drive everything from one source. Then you don't need to be changing the resolution of all of your noise operators. One thing we want to adjust here as well is the amplitude. So thinking about rotation, we're dealing with degrees. So 90, 180, 360. So we want to get maybe somewhere like 110 for a more, like a much larger rotation. I'll add a null and call this ROT for rotation. Grabbing my geo comp, I'll drag that onto rotate and type RGB. And now we start to see our boxes rotate based on this noise. Now, it's currently set to a very low period, which is how I wanted my position variance to be. However, I'm going to bring this up to 20. And now we're going to see more gradual changes in the rotation across the torus. This is very much something you can dial in to taste. So this is how I made that original effect, but you can play with all these parameters and get different effects and changes to that noise. All right, so going forward, let's also animate our rotation. I like often linking things to the timeline so I can make them loop perfectly. So I will start by just adjusting the length of my timeline, which to 1000, and the R end, just this slider here. Those two will affect the speed of everything. So if you later want to speed up or slow down the animation, you can just change your timeline and everything will correspond. I have done a more advanced tutorial on looping noise, so I'm not going to dwell too much on that, but I will quickly set that up. So I'll grab my timeline chop and also choose end, which is going to give me the length of my timeline. I can add a math chop, and in combined channels, divide those two numbers. So this will give me, I hit A and R to reset the bounds of that, or the range. This is a fraction that is linked very directly to my timeline. So this I will add a null, and I will call this fract. You can call it what you like. It might be fraction or timeline. This is just a shorthand that I use. Additionally, for my noise, I actually want to set this to simplex 4D, and I'm going to be transforming it in the Z and W axes, specifically using a sine and a cosine wave so that it can loop relatively seamlessly. To do this, I'll add a pattern chop, first sine, and then the second one I'll copy and make this cosine, using a merge chop to combine those, and then middle mouse button with a lookup chop. This creates a stem, and then I'll use these two sine cosine as my lookup table. What this does is you'll notice that as one channel slows down, the other one is at its peak speed as it goes through the center. So if we use both of these values to transform the noise, it will not slow down at any point and should feel like it's kind of continuously transforming, even though we are stopping at certain points as the direction changes. So I'll call this loop, which is what I'll be using anytime I want to loop noise. And I'll select that chop down here, right click to add a null, and then A to open the viewer and export those to my translate Z and translate W, or in this case, I call it translate T4D. So yeah, we already have, if you scrub along the timeline, you'll see that not only does it link to the timeline, but it loops perfectly as it goes across the end to the start. If we want to change the speed of this, we can add a math by right-clicking to add this in line. And then in the multiply, higher numbers will move faster. Lower numbers, you'll have less change over that duration. So you can find a speed that you like. I'll just keep this at 0.5. So the next thing we'd like to do is add some motion to the camera, so it's not so static. I can feed off of these same timeline-based values over here. In this case, I want the fraction. And because my camera is rotating, I want these values to go from in increments of 360. So if I want it to rotate once, that's 360, 720, etc. So I will use a math and set the range from 0 to 360, or 0 to 360. Adding a null after this as well. And there's some different ways to rotate cameras. I could actually have used something similar to this loop to translate it and have it like always look at the center. There's also the option of the path SOP if you want it to follow a path. In this instance, I'm going to use a null. So this is one of my favorite ways to make cameras orbit a single point. And so the way to do this, and I'm going to split this screen again with Alt left bracket, again, right here, and hit Alt 3, or you can use this drop down to get to the geometry viewer, just so we can see what's happening here. Is our null is centered at the 0, 0, and our camera 0, 0, 5. So actually 0, 0, 0 for our null. We want our camera to first off look at this 0, 0 point. So there's a handy look at parameter here we can drag our null to. Now if I translate my camera in other directions, you'll notice that the camera is always pointing at the donut, and the donut always stays in our camera. Setting that back to 0. I also want this to rotate when I rotate this null. And so this actually, as of some recent updates, changed. So there's no longer a constrain to parameter, which is how it will probably look for other versions. So if you're using an older version, you won't see this same dropdown. However, in this instance, we have a couple ways to define the parent transform source. So one is from parent hierarchy. So you could do this by dragging a connection from the bottom to the top connections. I'm going to disconnect that and instead be using specify parent object, which is closer to the constraint to parameter that I usually use. So I just find connections sometimes get a little bit messy, and it's nice to have these data link visuals. So, okay, so now it's parented to this null. And now if I rotate this null, you'll see that my camera smoothly rotates. It's almost like it's an arm. So you can think about it as like, here's my pivot point, and I'm rotating it around that center. Oops. Cool. So we should just be able to take this value and drop it right onto rotate, export, and now we're getting rotation around the y-axis. I might copy this for my z-axis to give it a little bit more interesting rotation. And you can always change these values independently if you want them to rotate more or less. So the next thing I'd like to do is have some more interesting lighting. I'll leave this open actually. You'll notice that at certain points, the particles are just black. The points are just black. And also we should add some more interesting color and post effects. So our light, first we can maybe give it a color. I think like a bright pink for one of my lights. And let's also make sure that it's one, I will choose cone light. So when it comes around again, you'll see that it does taper off a little bit. This is something you can decide between, see what you like, but it's a little bit different in that it has this kind of tapering effect. Additionally, I want to make sure that it's always looking at this center point. Just like the camera, I can go ahead and set the look at my null 3. Now, if I position this elsewhere, it's always going to be focused on my target. And I'm going to light this from 4 different quadrants. So let's start off by placing this one. I could do 10-10. I think in my example, I'm positioning them at something like 16-8. But you can play with this to get different effects and find something that you like. And now I will copy this and position different colored lights in each quadrant. So I can copy this once, and I will set the color, this one to like a cyan. Let's go back to the X form or the transform and send this to the negative X. So now we've got one over here. Let's do the same, this time positioning it in the negative Y. Change the color to green. And then lastly, the yellow light, this one is in the positive positive X, negative Z. So yeah, we have different colors from different angles now, so it's looking a little bit more interesting. I'm going to close my geometry viewer now that we've got those positions set up. And yeah, currently it's, it needs a little bit more to it. So one thing I like to play with is shadows. I'm selecting all of the lights right now, so right click to drag. So I'll play with them all at once. The shadow type, you could choose hard 2D mapped, and it already is pretty nice. I mean, we have darkness inside of the torus, so that's creating feels a lot more realistic. For my example, have soft 2D map, and this doesn't look different immediately, but we can start to get more of an effect by increasing the light size. So this is something you'll have to dial in based on, how close your lights are, how large your object is, all sorts of things like that. But let's bring this up to like 1.5, and you start to see a softer shadow. Additionally, I sometimes will increase the shadow resolution. It's not really noticeable in this example, but there are other times when you'll see artifacts in the shadow, and so increasing the resolution will often is one way to improve that. We could just multiply this by 2 for all of these. If you are encountering performance issues, this is one place where you could bring that back down to, it does take more resources to render the high resolution shadow. Cool. Additionally, we could play with the material a little bit. I believe in my example, I have a very high specular. So you'll see when I increase that, we're starting to get these little shimmers, especially when the cubes are kind of directly reflecting with the lights. And we could increase the diffuse as well if we'd like. So you can play with these two for different lighting effects. I also want to add some post effects to this. So in addition to our shadows on our lights, we can add what's called SSAO, or screen space ambient occlusion. So this is a post effect. It's happening after we render. And if we turn off combine with color, it's a little hard to tell because it starts off at a pretty low quality. But if we decrease the blur radius and change to full resolution, I'm going to pause this so you can see. You can tell that it's starting to add shadows in sort of the crevices of our geometry. So when different edges come together, or when we have different sides that are close to one another, it can be a nice way to make something feel a little bit more realistic. Note that this is a pretty heavy operator and process. So especially if you don't have a dedicated GPU, this can start to take a lot of resources to render. And that is especially the case as our render resolution increases beyond 1080 by 1080. As we start to increase the quality of our SSAO effect, you'll start to see this can take 4, 5, 6 milliseconds to render on your GPU, which is a significant amount of time. So just calling that out, this is one thing you can also reduce in quality to improve the performance of your render. So I'll hit play again, and let's just, I'm going to dial these up to 20 and 30. That just is usually affects the quality. You'll see kind of visual increases in quality as you increase those two numbers. Additionally, you'll see as you increase SSAO radius, it starts to change like the depth of the shadow, or rather like the radius from the different geometry that's affected. So instead of getting finer shadows in the crevices, we're getting like shadows in the inside of this tube. So that's going to have a pretty dramatic effect on the quality of your shadows and your SSAO. I'm going to keep this at 0.2 because I really just want this as a means to kind of add a little bit more definition to when these boxes intersect. We can also adjust the contrast. So especially if you're getting a lot of artifacts, bringing this down helps once you multiply it by the color. So once you've gotten that to a place where you're happy, then we can move on to adding some blue. So I believe this is pretty close to what I had. I might have a little bit more contrast in mine, but otherwise, yeah, looking pretty good, adding some additional shading. Lastly, I want to add some blue. So there's this new bloom top that's been added in the last several iterations of TouchDesigner. Previously, there was an image filter, and it's still here, called Bloom, which gives you some different options. So I definitely suggest checking that out, seeing how they differ. When might you want to use one over the other. In this instance, we're going to check out the bloom that's recently been added. I'll also add a constant by right-clicking to add it in line. Set this to black, output to over, and swap the order so that we have a black background now that we can kind of see a little bit more what the bloom is doing. So the bloom is an effect that kind of adds glow and bloom to concentrations of bright values or high luminance. So it even since I created this original sketch, we have had several updates where a lot of these parameters are new. So I'm actually still kind of getting a feel for what I like with these new parameters. But yeah, it's a handy tool, and you can already see how it's starting to add kind of like a nice quality when we have the bright points in the image. Some of those like specular flickers, right, are kind of catch it as well. So you can start to play with these parameters. I think the default actually looks pretty decent and it's close to what I had, but you can adjust the threshold, which that's sort of adjusting, how dark or light does the value need to be to get caught by the bloom or affected by the bloom. The pre-black level is sort of similar. So that's kind of passing whatever is getting passed into the bloom. The lower this value, the more bloom you'll typically see for darker values. So you can start to play with these different parameters and get different effects. I'll also point out the min and max bloom radius. If we pause this, like if I bring down the maximum the min especially, you'll start to see like we're getting a tighter bloom, right? The glow is a lot tighter. And if we include both of these with a large range, you're going to see both of those combined. So there's a wide radius and a tight radius at a gradient. Whereas if we bring this all the way up, it almost is too large, right? You're not getting that tight bloom around some of the brightness. So that's something that you can adjust to start to dial in the quality of the effect for your taste. Here, I'll go ahead and hit play. So, yeah, we're at the point where we've got ourselves a nice looking instance to Donut. The next step is to add our attractor that can, push and manipulate these instances more dynamically. So I'm going to jump over to a quick example I prepared to talk a little bit about what that means, and then we'll look at adding it to the system. All right, so here's a quick little demo I created that shows the effect we're going to be creating, except here it's in 2D instead of 3D. I just want to show, I think it'll be a little easier to understand before we dive into doing it. So this red point represents my attractor, and as I move it, my instances at a certain radius are getting sort of pushed away and then also pulled in, or rather staying, I still can move across them, right? So they're getting pushed away, they move across the attractor and then back again. And they're also scaling based on that radius as well. So as they get closer to the attractor, they get smaller and then back to 1 at the radius of the effect. So you can see that if I turn on draw radius, that effect is activating as it's a certain distance from my attractor. So if I turn off the scaling and the many points and only look at my original point here, so we've got 1 point, I've got my radius. That's the radius of my effect. But I also want to know when this point is inside of that radius. So one thing I can do is calculate the distance. And so that can be done with the distance formula. We'll look at that later. And then additionally, I also want to push it based on the direction. So that direction is the vector, this blue line, and that can be found by subtracting the 2 points. So that gives us where I want to push and the amount that I want to push that dot. Currently, I'm sort of scaling it in this funny way where it like pushes outwards, but then it's also like the magnitude is related to the distance as well. So it only engages like once I am in that radius, but then the closer that I get to my attractor, it actually stops affecting the original position, right? It's moving closer to that original, and then again it moves out and then sort of back again. So it's this funny little out in effect, but I do think it looks pretty cool when we have a lot of points, even if it is sort of funny on its own. So yeah, those are the sort of key components. And then once we add, if I add many points, it's pretty funny. Yeah, once you add a bunch of them, it gets a lot more interesting. And then additionally, we can make it so the points scale as they get closer to that original point. So again, that's kind of based on the distance that we're calculating. When it's equal to the radius or greater, our points are all 1 in scale, and then they just get smaller to the point that they're 0 when the radius is, or the distance is equal to 0. All right, jumping back to our instanced donut or torus over here, let's go ahead and add that attractor system. So the first thing we need is the point of the attractor that's going to move throughout our donut. I'm going to create what's called a Lissajous figure. So that's a combination of sine waves at different cycles that create circles or other kind of wave patterns through my donut. You can certainly use different patterns if you'd like. So to do this, I will be using chops. I'll copy my pattern 1 and give this 4 cycles. Copy that again and give it 5 cycles. I'll also name these something useful like TX and TY since they represent translate or positions. I'll merge these with a merge chop. And then I want to use this same lookup setup here since I want my motion to be locked to the timeline. So now using this merge for the lookup table. I'll add a null, right click to add a null and call this ATTR so I can reference it. And then now I also want to be able to see that point moving through. Just for debug purposes, you can keep it if you'd like. It is sometimes interesting to show it or hide it like I have in my original example. So to do this, I will create a sphere, SOP, make it a bit smaller, 0.1 for the radius, right click on the output with a geocomp, and then hitting A to open up the viewer, just drag those onto translate and export TY and TX and TY. So you should see, yep, you can kind of see it there. It's a little hard to see because it's being lit by the same lights and setup, but I can make it a little bit easier to see by just adding a constant chop as the material. And it does sort of glow nicely, so that's actually something that can kind of be fun. I've played with that a little bit in other sketches. Okay, so we have our attractor position. The next step is to add the actual attraction. I'm going to do this in 2 different ways. First, I'll show how we can do that only using tops and do all of our math in tops, though I find that method a little harder to follow and read. And these days, I'm primarily doing my work in GLSL for these types of purposes. And so after we do it in tops, I will go through how we might make the same thing in GLSL instead. Okay, so we're going to add this to the position values since we want to be first moving them away from our attractor. So I'll start by right-clicking after this noise 1 and choosing a base comp. So we want to basically work inside of this just for the sake of organization. I'll call this ATTR tops, and we can jump inside. So you'll notice this automatically has created a new sort of base for me to work inside with, in and out automatically created. The next step we want is to grab our attractor and have that in tops instead of chops. So I will create a select chop, and I'm just going to type the location relative to where I am right now. So ... / goes up 1 level, and then I named my chop ATTR. So it should just grab that chop directly. You can also do things like split your screen and drag it, or create an input like an in chop. However, I often am using selects since I find it to be not only a clean way to work, but also forces you to think about the organization of your network. And I find that it's a good practice. So let's add a null after this. And there's different ways to go from chops to tops. I could, for instance, just convert it with chop 2, though when we're time slicing, this can get tricky. And so instead, I'm going to take a constant top and simply map these to the values. So my constant, it doesn't really matter what resolution, but I will set this to 1 by 1. And additionally, make sure I'm using a 32-bit float pixel format. Now for the constant itself, this null, I can open the viewer and just map these with export chop and export chop for X and Y. So my red and green channels represent my X and Y positions of the attractor. And for now, I don't care about blue, which is our Z, since we're only translating into X and the Y, but you can always add an additional channel in the same way. And all of the math should hold. So the next thing we want to do is get the direction, which is the vector. If we subtract these two, the point from the attractor, we'll get a vector that is pointing between the two. And so let's start by doing position minus attractor. So I'll grab a subtract top. There we go. Sorry, set that to full. And you'll notice that when I plug this into the second input, it's made my size 1 by 1. So we want to make sure we choose the fixed layer as 1. And then another thing that's gotcha is making sure that we choose nearest pixel for the input smoothness and viewer smoothness. Otherwise, it will interpolate this value across the image, which is not what we want. We want it to be set to nearest pixel. All right, so let's add a null after this, subtract, and we can call this dir for direction, just so we can follow this network later. Next, we also want the length. So the direction is how we will push them away from the attractor, and the length is what we need to determine if it's within a desired radius. So to get the length, we can do this in one math top. It has the option of combining the channels and length. So also like distance, length, same thing. And I think I called it distance previously. So we're going to also need to combine the channels. If I get A and then N, right now, 0, 0, it shouldn't have a great effect, but if there was some values in our alpha, it could potentially affect things. So for now, let's only combine RGB for our length calculation. And then the output, right now, these are all still different. These second two are probably identical to my input. And so I want to just set RGB for all of these. You'll notice once I do that, they're going to be identical to my first channel. So we don't want other information in here that's not our length calculation. I'll hit N so I'm not looking at that split view. I'll add a null afterwards and call this length. Sometimes I will color these. So if you hit C, you can make these red or blue or something, just so you're aware that they're not only nulls, but they're sort of important information that you might select later. The last thing we need here to calculate is a sort of like magnitude for our effect. This doesn't have to be what I'm doing, but this is just what I've chosen for this specific effect. So I want the effect to engage at a certain radius and get stronger as I get towards the attractor itself and be disabled outside of that radius. So it's not affected unless it's within a certain radius of the attractor. So one thing we haven't done yet is define what that radius is. I can go up a layer, customize this component, and just add a radius for my float as a float. So now I can just go here and later change this value easily without diving in. So I'll set that to 0.8 for now. And next, I'm going to take this length or distance and divide it by the radius. What this will do is set it, it's sort of like a normalization where at the radius, when you divide a number by itself, you get 1. As we move towards the center or towards the attractor, our distance is going to decrease. And so that will be approach 0. So we're getting this sort of 0 to 1 as we move out from the attractor to the radius, and then anything outside of it will be negative, and we'll clamp that at the end of this. So the first step is dividing by the radius. We have our math that can do this. And there's not a divide, but essentially I'm going to multiply it by 1 over the radius, which will have the same effect. So I can type parent.pair.radius with a capital R to get that parent parameter. And then I also want to, in this case, I'm going to take 1 and subtract this value. Since actually I'm looking for this effect to get larger as I get towards the center. So right now, instead of it being 1 at the radius and 0 at the center, if I take 1 and subtract that value, it'll flip that. It'll invert that range. So I can do this with a constant. Actually, now I'm thinking I could probably do that with another math, but this is how I did it originally. So let's just make sure this constant is set to 32-bit float. And if I want to keep this the same sort of size, I could also kind of chain these and make sure my combined input is set resolution only, or we can just be careful when we're compositing them. So if we keep it this way, I will choose subtract. So 1 minus our 1 over radius, or 1 over, what length times length over radius. And then here, let's just make sure we use nearest pixel. And looks like it's getting the right resolution and format. And you'll notice that now these values look like there's some black and white, which is good because as this is moving through our points, we should be seeing some flickers of white. If I hit A and then N, we're also getting negative values. That's where it's outside of our radius. So the next step is just to limit these values with a limit top and just add a clamp that goes from 0 to 1. So now if I set this to nearest, just to view it a little bit cleaner, we only have 0, and then anytime it's affected in that radius, we're getting values that go from roughly 0 to 1. Sometimes it's not even close to 1, depending on where the attractor is. Cool. So that's looking good. Let's add a null and call this just mag for magnitude of our effect. And I will call that blue. So now we have the pieces that we need. We still need to manipulate our points, however. So the first thing I want to do is I want to push them by this direction. And one thing to note is this direction is not normalized, meaning as we get close to the center of our attractor, the effect will be smaller also because this direction is smaller, which I think is a cool effect, but you could always play with normalizing this to get different effects. So let's multiply those two. It's off the screen there, but that is my direction. And then next, I also want to add that to my final position. So I will add an add, and let's get a little on here. See what happens. Oh, there you go. Cool. So it worked. You'll see that they get kind of pushed away pretty naturally by the attractor. So that's exciting. It worked. There's a couple other things that I do want to do. One is I'm going to output my direction as a second output, because I do want this for some additional things I'm going to look at. And then lastly, I'm going to send this magnitude out as well. Now, later, I'm going to be doing this in GLSL, and so I'm going to keep this format similarly. It might not make a lot of sense why I do this reorder right now, but later when I do it in GLSL, I'm going to be storing my magnitude in the alpha, and so I'm going to keep these two systems as consistent as possible just so that we can see the translation. Since I technically went GLSL back to this example here. So let's add a reorder Oh, I spelled that wrong. Reorder top, which lets me basically I can take my magnitude in the second input and set that red channel as my alpha. So now I have the positions that I care about, and then I'm just kind of sending that alpha out on the same channel. All right. So the next things I want to do, one is I want to scale these so that when they're close to the attractor, they get small, kind of in the example we looked at earlier. So to do this, I'm going to grab a reorder again. This is kind of why it seems funny. If I was only doing this system, I might just send this out as an out, this magnitude value, but this might make more sense later. So the I want this to only be my alpha channel. And so I'm reordering it so that my alpha is all 4 channels. I also want this to be small when it's near the attractor and everything else to be 1. And so this is the opposite at the moment. So I can use a mask to just flip that range. So going in the range, 0 to 1, 1 to 0. Now I can go ahead and just create a null, and this can be my scale. So I'll go ahead and for the scale op, drag this in and type, this can be RGB, or I'll do that just in case, you might want to vary it in different ways, but this also could be RRR if you're only going to use 1 channel. One thing that I think is a nice touch is to give it a little bit of an easing. Right now it's just strictly linear, but we can use a lookup top and a ramp to start to control the shape a bit further. So if I hit P here and just choose, instead of interpolate notches, linear, use ease in, out. It doesn't have a dramatic effect. Maybe I can pause it. Yeah, very subtle, but it bulges a little bit more here, and it's going to have this kind of S-curve shape as the scale tapers off. Cool, so I'll go ahead and hit play again. We're running out of space here a little bit. I'm going to reorganize slightly. All right, so next thing, one thing that I liked was rotating all of these instances to the attractor. So as the attractor moves, the whole entire thing is shifting a little bit. And so to do that, that is why I sent this direction out my second output. So let's just grab this as a null and bring this down a bit. And I can call this rotate 2 or rot 2, as I abbreviate it often. And this has a handy option to rotate to vector. So what this does is it kind of points, just like we were using this look at function over here to point the camera or the light at a specific point. We can also do that with instances if you wanted everything to point to one spot. So I'll drop this in here on the rotate op and choose RGB. Oops. And sometimes we also need to adjust this order. I find when you're using other rotation, rotate and then rotate to vector will let you first give it its own rotation and then apply an additional rotation. If you do it the other way, it basically just often doesn't have any effect. So, okay, so you can kind of see what's happening. One way that we can really see this in more effect is if I just temporarily turn off my rotation here by, you don't have to do this, but multiplying my rotation by 0. And even if we want it a little more extreme, you can already see that they're rotating towards the attractor, right? But we could adjust this in like no, I don't think it's the Z. It's probably yeah, it is the Z, but we'll see what direction makes sense. Yeah, you can see it. I don't know why I was getting confused by this earlier, but yeah, the Z, now they kind of all point at the the sphere, which is also a fun effect. So this is something you can play with further, like making it really skinny. Oop, too skinny. So I'll set that back to 0.04 for now. And we'll also delete our math, but just as a demonstration of like what's happening with that rotate to option. Okay, so the next thing I might want to do, this is just another really subtle touch, but I think it's all about the details, is I think it's interesting when that original rotation is like disabled when it's within this radius. So things in the radius are strictly rotating to vector. They no longer have that noise-based rotation. To do this, we already have information here actually about when it's inside the radius. And this is like, it's almost like when we could just take this and multiply it by our rotation right off the bat. And so one thing I will do is I'm going to give myself a separate lookup table for this. I'm just going to copy this lookup in this ramp, just in case I want to dial in this effect further. And then we'll add a multiply and drop this here. So very subtle, but we pause, you should start to see it only affected when it's close. One thing we can do if we want this to be more pronounced is like dragging the my ramp further in this way, so that this is like the attractor on the left to not being attracted at the radius, if we think about this left to right. And so this means that a larger portion of my attractor radius is going to be nullifying or multiplying my rotation by 0, basically muting that. So this has a little bit more pronounced. You can actually start to see that effect happening if you look carefully at the rotation of boxes. So yeah, that's essentially it. If you want, you can even stop here if you're unfamiliar with GLSL or not wanting to dive into it. But next, I want to look at how we can do the same thing in GLSL. GLSL is a shading language that has a syntax based on the C programming language. It's notoriously challenging to wrap your head around. It took me quite a bit of time, and it's also what all of these tops are using under the hood. So this is not going to necessarily be in like a full beginner intro to GLSL, but I think there's value, even if you've never touched it before, to see kind of a practical example. I didn't actually really get my head around it until I started hacking and exploring and like playing with all of these different examples in TouchDesigner, and could see kind of like how the code that I wrote related to the final output. If you want a good intro, I rather enjoyed the Book of Shaders, which I'll link to in the description of the video. So to begin, I'm going to adjust this view a little bit. First, create a GLSL top. I have a middle mouse button here to branch. So this is going to be my operator where I do everything I did inside of the attractor tops. And I tend to like editing. You can edit directly in this DAT by hitting A and typing it in, and it has nice coloring now. I will typically edit in external editing files, which you can set up in your settings, an external editing program. So I'm going to use Sublime Text. I hit Control E to edit it. So we can pop that up left and right, so I can see my network and my code in the right. Right now, you'll notice that it's all white. That's because we're setting our color to a vec4 of 1, which is 1 for all channels. It's similar to doing 1, comma 1, comma 1, comma 1. So that's just a shortcut for saying every single pixel runs independently and it just sets it white. Instead, I don't want that. I am going to use a vec3 in this case because I only care about XYZ or RGB. And I'll call this position. And this texture function is sampling my first input. I'm sampling it at vuv.st, which is the position of that pixel. So it's basically each pixel here is just sampling the pixel that's at the input location. So I'm going to get a copy of this if I just do vec3 position XYZ or RGB are identical ways of getting those first 3 channels. And then lastly, I need my output. So I can just do this right here, vec4 position. And because this is a vec3, it only has 3 channels or values, then I need to make sure I add an additional value. It will combine all of those into a vec4. So I'll just send out, for now, y as my alpha. And if I hit Control S, you'll see that, this should look identical. So that's the first step, is getting that in there. We also need the attractor position and the radius. So that's what we can do with uniforms. These are ways we can pass in information through this vectors tab. So anything I name here needs to match in my code. So I do want a uniform vec3 because I may later, you might want to add a third dimension to our attractor, and I'll type u attr underscore u is a convention for uniforms. So that's a good way to know if something is a uniform. I also want a uniform float for our radius, and I'll call that urad. Very congratulatory. And let's see, uattr. So let's put this here. And I'll hit plus and add urad for my radius. So I could just set this to also what I had for my tops. And for uattr, we want our attr, our attractor value. So I can hit A here. And I'm just going to drag this onto attractor, leaving Z for 0. Though you could always, change this if you want to move the Z position of your attractor. Just don't forget, if you add a Z here, you need to add it here as well. Okay, so we should have both of those values in here. Now we'll go back into our tops just so that we can see what we're doing. So the first thing we did here was get the direction. So in a similar way, we want to, in this case, my direction is also a vec3 because it's a vector in 3 dimensions. And I want to call this dir. So I'm naming the variable. And then this is just our position minus our attractor. So, there we go. So that should do it. Now we also want that magnitude up here. And in the process, we'll get our length. I don't use the length elsewhere. So I'm just going to calculate all of this in one line. So float, because our magnitude is really just one value between 0 and 1. I'll call this magnitude, if I can type. And we'll set that equal to, first, we want the length. So that's, we can actually do with length is a function that will just give us the length of a vector. And I'll type in dir. We also take that length and we divide it by the radius. So I can divide this by our urad, uniform. The other thing we do is we take 1 and we subtract length over the length of our direction over the radius. So to do this, I can just do 1 minus, and that should do the trick. And then lastly, we limit it, right? We're clamping this between 0 and 1. So there is also a clamp function, and we can use parentheses here. And then I'm adding, I haven't been talking about the syntax, but semicolons are essentially your periods in C syntax or C-like syntax. So make sure we don't miss that. Great. So that is looking good. The next thing I want to add is adding this to our, multiplying this by our magnitude. So this is like magnitude times direction, and we're adding that to our position. So we can do this again in one line. I will just say position, and I'll use plus equals, which is saying I want to set my position to itself plus something else. And this can be dir times, there it's showing up, magnitude. And then I'll also put my magnitude in my alpha. So you notice that that's essentially what I was doing with the reorder, was just making sure that my output here will be the same as my GLSL. It's not that important, but I think it makes some consistency between the two that you can follow. So if I go up a level and just see what happens if I hit save. Oh, error. So what's happening? I probably made a typo. Clamp. No over. I totally missed. I just missed this. So clamp, beyond just needing the value, I also need to tell it what the minimum and the maximum is. So I'll do comma 0, comma 1 for my min and max. Okay, now it's working. So that's great. And actually, I could add a null by right-clicking here. And I can see if it looks close, but let's just see if it's functioning the same way. Great. So look, it's identical to this first output. Now, one thing we're missing is this rotate 2, right? So I could, make a separate GLSL top, or I could keep this if I want. There's also a way to output multiple buffers. So if I want to output, they're called color buffers. If I want to output 2 of these from this shader, I can. I just need to change a couple things in the code to line up with that. So the first thing I need to do, this is, I'll also link the, you can find this, there's like how to write a GLSL top article on the derivative documents that I sometimes still have to go to because I don't always have this stuff memorized. So there's definitely useful documentation on this, but you want to type layout location equals 0, and then out vec4, and I call this OPOS for out position. So you'll notice that this is identical to our current, this is declaring our frag color as our output. This is telling us that color also wants to be, this new one I'm creating wants to be located as my 0th color buffer. I will delete this top one and copy O position to the bottom so that this first output is I save, no errors, it's still working. And now I can copy this layout location equals 1, and I'll call this ODIR. And then lastly, I want to add that ODIR, set this equal to, let's copy this TD output swizzle. This is good for making sure things work on cross platforms, things like that. So do leave that. And let's add dir. And then doesn't matter what we put in our alpha. I'm not using it. You can set this to 1. Hit save. So great. Still no errors, but where is that? where do we find that? So this is what the render select top can be used for. One of the things it can be used for, at least. And so I will grab my GLSL, drag it onto the top. Currently, it's still just looking at the 0th buffer. You can see this index here, but if I set 1, okay, now this actually should look identical to my dir, or yeah. So if I drop that in, you should see it also function. So there we go. That's how to do it in the GLSL top. You'll notice that, I personally prefer this now that I can read it more fluidly, but also just because I find it easier to read and a lot faster to edit and work with. I can disable, I can comment out a line or copy and paste it, look at it later. So especially for things that are manipulating particle systems, I generally prefer it at this point over something like this, but this also has the benefit of not involving any code. And so there's plenty of reason that you might also be doing math in tops. And I do a mixture of the two. It really depends on how much I sort of want to do in one place. The other reason that you might do this is if we middle mouse button over onto our operator, it does tell us kind of roughly what the GPU and CPU cook times are. You'll notice that this has 0.012. It's not very much. That's like a pretty small cook time. And similarly, this has a 0.05 cook time. And so the big difference here is like, well, we're doing the same thing, but there is a pretty I know these are small numbers, but once we get to say like larger textures that aren't just 100 by 100, this performance definitely scales when you get to much larger operators in texture size. And so this not only can be used to optimize the GPU cook time, it takes a lot less RAM as well. So each of these operators has an additional RAM footprint on your graphics card, this memory allocation. So it's just some things to note, kind of like more advanced topics that, especially if you're a beginner, I wouldn't worry as much about this, but there's definitely good reason to start kind of thinking about this as soon as possible, since from my experience, it can take a while to wrap your head around its uses. All right, that wraps up our tutorial. I want to do a quick overview of the project file. So this one has two nodes here, or two bases. One of them, in case you want to play with it, includes that example file that I was playing with, showing the attractor math in 2D. So definitely, if you want to explore that, there might be some fun things to gain in there. On the right, we have our particle donut example. The network is likely very close to what we just did. I'm pretty sure there's probably a couple small things I did differently, but for the most part, it's there. I am trying to add some comments here and there just to kind of organize things. Additionally, you'll notice that I'll click this attractor, particle donut view here so you can see on the right. One thing that I added were a few toggles to disable the SSAO and bloom and to hide and show the attractor. I'll save it with some of these just down, like off, and also probably reduce the number of points to a smaller amount just so that, it has less chance of kind of causing performance issues if you don't have a powerful computer or GPU. So that's just a note. One thing that you can do to then start playing with this, I mentioned this early in the tutorial, but you can certainly try different, our attractor doesn't even show up, but you could try different shapes, right? And see how that affects the output. So all of these are going to work. It's just changing the positions in our starting position. Another thing you might consider trying is, in our either of these really, but if you want, you can switch between them using our these two switches I added. So if you want to start playing with the logic for the attractors, you might say, oh, what happens if I turn off this limit, right? And I did something that broke. Oh, I disabled this constant. There you go. So, what happens if we disable this limit and you get something kind of wild? So, there's a lot you can do to start kind of manipulating, playing with like the attractors. How might you color, say, the instances instead of using the light to do that? What if you're coloring it in this instant tube tab based on this same proximity to the attractor, right? So that's a good exercise to try. All of these things, really up to you as to how you want to explore this system, but I do hope that you find ways to kind of play with it and make it your own. So hopefully you got something out of this tutorial, and thanks so much for watching.